All right, everyone, we are back, and we are going to do our second problem. Bend, don't break, ceramic material, length of this, width of this, thickness of this. So we're going to basically be setting up, let's see, our coordinate system, x and y. Let's set this as x equals 0, y equals 0. Nice symmetric boundary conditions. So we have e dot I dot y quadruple prime equals, we're going to have our Dirac delta, or excuse me, let's just delete that there, minus 1.3 times 10 to the 3 newtons Dirac delta of x minus L over 3 plus 5 times 10 to the 3 Dirac delta of x minus, this is x equals L, excuse me, minus 4L over 5. Fantastic. So we have our expression set up. We also know that y of 0 must be equal to 0, and that boundary condition must be equal at y equals L as well. We know the slope must be 0 here, y prime of 0. There's going to be a resultant force here and here, resultant moment, some direction here and here. Statically indeterminate. We have to use our Euler-Bernoulli bending problem. And let's get to it. Ceramic beam, 300. Width 25 millimeters, 0.17 for our thickness, 61 centimeters in length. Fantastic. We are going to do minus 1.3 times 10 to the 3, and that's x minus L over 3. This will be x minus 4L over 5. And then finally, we'll have 5 kilonewtons. Boundary conditions, y of 0 equals 0, y prime of 0 equals 0. We'll also set y prime of L equals 0. This equals 0 here. Solve for our function. Actually, I need to go back and change a couple of things, but we'll do that later. Shift enter. Let's make sure our solution looks okay. Yep, this looks pretty good. We are trying to, actually, excuse me. I think I missed a sign here. Yes, I did miss a sign. That does not look okay because it should be pushing up, or at least kind of one part pushing up and down, all that good stuff. So now let's put this in here. Now let's go over here. That looks much better. Trying to push down, overwhelming force up, fantastic. If I want to find the maximum displacement, I need to find maximum and I want to search at 0.4. That looks so good. That's our maximum displacement. Maximum stress. Let's look at our moments. Our moment will be maximized. We have our shear too. Our moment will be maximized right at the edge, at the very end. So let's go to find maximum, and let's go ahead and search at, let's say, around 0.6. We have this, so let's justify the sign here. If I'm looking at the top of the beam, if I look back at my deflection equation, I'm actually in positive curvature here, meaning the top should be in compression, and we're in happy face mode there. So, and indeed we find it. Fantastic. Excellent. So, this is good, this is good. Where's the shear force maximized? We can look at that. Let's find out. Shear force looks like that at the end. So we're maximized at 4,142.96 Newton meter. That occurs anywhere from that last cut in that L over 5 region. But again, make sure you can justify that sign as well. All right. So what else do we have here? Excellent. So I have mystery material A, tested two materials B and C. Material B is viscoelastic. So number one, what type of material is this here? So this is my G prime, this is my G double prime. This is a pure solid for material A. So material A is a pure solid. I'll have to ask an additional question about that. B and C, B is viscoelastic, and C is viscoelastic material. And material C behaves like a viscoelastic material that is more liquid than material B. So they're both viscoelastic, but C is more liquid than B. So I'm going to do, this is going to be my B. When I do dash, I'm going to do G double prime. When I'm going to do solid, G prime, and this will be my material C. So C is more liquid. So what we're going to do, I'm just going to draw it like this. So material B, if I look at frequency, at high frequencies, so I'm going to do this here. C is more liquid, so I'm just going to go then finally here and here. Now, if I'm ranking, this will be my relaxation frequency here. Now, for material A, I'm just a solid. So for material A, my relaxation time tau is going to be basically infinity, and the TG will basically be infinity like as well. Infinite relaxation time. But if I'm material B here, and this is material C here, because I'm more solid than more liquid, my relaxation frequency of B is less than my relaxation frequency for C. Okay, we know that, and we can kind of call it star. Our relaxation frequency is inversely proportional to our relaxation time tau. So if my WC is very large, that means that my tau of C is less than tau of B. So, does this make sense? Yes, because my relaxation time should be longer for B because it's more solid. And similarly, my TG of C will be less than my TG of B. And there we go. I'm definitely going to also ask about what is material A as well, and make sure to include that. Fantastic. But that's it. So we'll see you in the next problem. Thanks. Bye.